So we can kick it off here. Thank you everyone for coming. This talk is going to be on the Elastic Stack, not in general, but as a specific security use case. So as you may or may not know, the Elastic Stack and Elasticsearch itself is a very, very broad tool that can do tons of awesome stuff. But the motivation for this talk and a class that I teach is kind of based there. This talk is based on. That's like 14 hours long and much more in depth. It's sort of difficult to figure out exactly what features apply to you when you're trying to do it for security. So I'm going to try to condense everything down as much as I can into an hour, which is a totally absurd thing to try to do. But I've packed as much as I can into understanding Elasticsearch into an hour as possible. How many people here have used Elastic like at all? Okay, awesome. How many people are using it like day to day? So 2 of us. All right, perfect. So a lot of new people. Awesome. So first of all, who am I? My name is John Hubbard. I used to work for GlaxoSmithKline as their SOC lead up in Collegeville. I am now one of the certified instructors for the SANS Institute, and I teach a number of their classes, pretty much most of the stuff from the Blue Team operations curriculum, all the stuff that would go with like Blue Team and SOC type work. So I'm writing a new class called Sec 450, Blue Team Fundamentals, which is going to come out in July, which is going to be for people who are like entry-level, getting a job like out of college or something like that, their first job in a SOC. We also wrote a class, me and Justin Henderson, called Sec 455, SIEM Design and Implementation. That course is what this talk is born from. This is just a 1-hour version of that course as best as I could do it with a lot less detail because trying to cover this in 1 hour is crazy, but I'm going to try to do it anyway. The other two, 511, 555, SIM-oriented course, and 511 is kind of like senior analyst, threat hunting type stuff. And my goal is to basically find the best tools and process and technology and share it with the community, right, through SANS and through everything else that I try to do. So this information and the tools and stuff that we'll use here is in a quick demo that you can put together with Docker, and I posted that at that link, and it's on the meetup page as well if you want to try to figure how to put this back together after class, because we'll have the video and everything. So first, let me back way up, right? What is a SIEM? How many people know what a SIEM is and use one all the time? All right. So a SIEM, in general, is the solution for how do we get logs from everywhere, all over an organization, get them in one spot, and then make them better, do visualizations, sort them, and keep them over time, and then try to find bad things that are happening in those logs, right? So that's basically what a SIEM is doing for us. And the order that it's going in is we have all of our log sources, right? Everyone's laptop, every server, every network switch and router and everything else. All of this is throwing data at a log aggregator of some sort. Every SIEM has something that does that particular function, and it's just going to receive data from a bunch of disparate sources, put it together, and then funnel it into some kind of storage mechanism. Now, I also said there's a queue here. You may or may not have that as an explicit piece of this, but it's to make, if you have like a DDoS attack or some giant event with just flooding logs in, it can queue up there and then not overload the storage and indexing that needs to come next. So ultimately, after all the logs go to one central location where they're parsed and various things are done, they have to get stored for a long time. Not only do we store them, we're writing the raw logs, but we also are indexing them into some sort of database to make it faster to search, basically as fast as possible, right, is the goal. When I'm saying, did anyone go to a bad website? You know, there's website X is bad. I want to search for the last month. I want to get that answer as fast as possible. So we use various ways of indexing it, and each SIEM does this in a different way, and Elasticsearch is particularly good at doing that. Then, ultimately from the storage, the last piece, we have some kind of front end, so a web page or whatever it may be that allows us to type in our searches. It allows us to create alerts that we can say anytime you see, X or Y happen, send an email to us or, alert me via Slack or PagerDuty or whatever, right? All those things. So in general, this is what a SIEM is doing for us, right? All SIEMs kind of cover this ground. The Elastic Stack covers all of those things, but it can do a whole bunch more. So we're here to discuss how to make the Elastic Stack, which is capable of a whole lot of things, do what we were just talking about. It's made up of those 4 main pieces, right? There's a collection piece. It's an agent that sits out there, or it can just take in logs from your routers like Syslog and that kind of stuff. There's an ingest piece, which is called Logstash. Storage is actually done by Elasticsearch itself. And then the visualization and search piece is done by Kibana. Quick history of Elastic. It was invented in 2010. There's a guy named Shay Bannon. He wanted to make a recipe search engine for his wife that was in culinary school. And he was trying to use this project called Apache Lucene, which was really, really difficult. And so he's like, I'm going to make a program that is a wrapper for Apache Lucene because I don't want anyone to ever have to use Apache Lucene directly again. And thus Elasticsearch was born, and it kind of blew up from there, right? So it's a way of making multiple versions of a search engine called Apache Lucene in reality work all together. And so you can scale out all of the data you're trying to search. But ultimately, Elasticsearch is at the very bottom layer Apache Lucene. So the company was founded in 2012, and as of 2019, it's one of the most popular products out there, projects on GitHub. It's open source. It's free. There are some commercial features you can purchase from them. In some cases, you do or do not need to do that, depending on what you need. But this is used by many, many companies for many use cases, not just security. But it is not like some weird fly-by-night open source project, full company behind it, support, and all that kind of stuff. So how does Elastic line up with the functions that we talked about earlier? Basically, there's these four main pieces. We have Beats. Beats is the agent that will sit like on my laptop. If I was in my organization, it collects all my Windows logs and any text-based logs, and it sends them in to the aggregator. The aggregator in this case is Logstash. At Logstash, we can say listen on ports, take in stuff from files, and we can specify various different types of inputs. We then use what's called plugins in Logstash to parse those things out, and then ultimately send them down to Elasticsearch where they're stored permanently. Then everything that's stored permanently in Elasticsearch gets queried from the front end, which is called Kibana. So this has a web page. We type in the stuff we're looking for. It converts that into a query that goes to Elasticsearch, and then the answers come back, and we get it from Elasticsearch, rendered back on the screen. Elasticsearch is actually just a web server. It is not doing anything fancy, at least to you. It's got an API. It runs on port 9200, but it's just doing HTTP transactions with JSON objects. So we're sending in a query as a JSON object to a web server with GET requests and stuff like that. We're getting back an answer, and that's all that's really happening there. Elasticsearch is a web server that can do that sort of thing. Now, if you look at the Gartner Magic Square, you will not see Elasticsearch on it. So if you came here thinking, I'm going to figure out how to convince my management to go to Elasticsearch as a SIEM, this is one thing you might run into, and I like to point this out. They don't market themselves as a SIEM for various reasons, one of them being, at least what I was told, that they are not interested in putting themselves in that bucket with SIEMs only, right? Because they can do so much more. They're really a search engine, right? So it doesn't really make sense to put them on this list. If you ever look at the Magic Square, you're not going to see them there. But if you look at what Gartner says, and the almighty Gartner, right, what is a SIEM? Well, it supports threat detection, incident response, historical analysis of security events, a wide variety of event and contextual data sources, reporting, incident investigation through analysis of historical data. Elasticsearch does all that stuff. So it's pretty hard to argue that it's not a SIEM. But every once in a while, you run into people that want to have an academic argument about the definition of what a SIEM is. And my response to that is, does it help you find bad things and do all this stuff? Yes. Okay, great. Then we'll just call it a SIEM because it gets the job done. And it might do it for free and save you millions of dollars a year. So maybe you should try it out, right? So as a SIEM, Elasticsearch is very, very good. There are companies that do it with great success, so it's hard to argue that it can't do that. It collects all our logs, it indexes our logs so that we can search them ridiculously fast compared to every other SIEM that I've seen, actually. It can do reporting and alerting and all that kind of stuff. We can put on security features to it. It's RBAC securable. We can make roles and all that kind of stuff and let analysts do analyst stuff and let admins do admin stuff. Machine learning, right? All those fancy things that everyone's like, oh, we have machine learning, buy our product, right? This one is actually really good. I like how they do machine learning because they're not like, it's a magic box. You pitch stuff in and magic comes out, right? It's time series. It's a reasonably done machine learning. If we have time, I'll do a demo of that. So what we have in terms of how logs come in, raw logs, whatever, a multitude of sources over here, maybe a Beats agent, a whole variety of different things go into Logstash. Logstash does its thing. It goes into Elasticsearch where the logs are stored permanently. And then it goes, and then we go to Elasticsearch where we're able to query and do searches and visualizations on all the stuff inside Elasticsearch. So that's the 50,000-foot view of how all of this works. The Beats portion in particular, This one is special because there is a bunch of different kinds of beats. It's not one program. It's actually broken down into WinLog beat and file beat and all these other beats, right? Beats is a framework and a special protocol to get stuff dependably to Logstash. So you can send Syslog stuff directly there, but if you want to do it better, you use beats as an agent to pick up the files that have the logs in them and then use the beats protocol that can say, hey, Logstash, are you too busy? Oh, you are? Okay, I'll slow down for a little bit, and I'll buffer, and I'll encrypt and compress and do all this stuff, right? It's just a better way of sending stuff. The way they've worked it, though, is every single individual type of file source you might want to pick up has its own beat. So if you're picking up raw files, you use file beat. If you're picking Windows EVTX files up, that's WinLog beat. There's packet beats if you want to pick up network data, audit beat for command line stuff, function beat if anyone's using serverless architecture, that's one of the brand new ones. Journal beat is going to be out there for the Linux journaling system. And then they've also open sourced this, so you can write whatever beat you want. And there's stuff out there for snort alerts and bro and various other things. There's a big list of them. Okay, architecture. This is probably the most complicated piece of explaining Elastic. When you go and try to learn this stuff, I've tried to make this as simple as possible. Three main terms you will hear a lot. One, cluster. This is the top level item. A cluster is an entire group of nodes running Elasticsearch as a process, right? Elasticsearch is a program, you download it, you start it up. That is technically one node, and you could start two processes of Elasticsearch on one computer and make two nodes, but that wouldn't make any sense because they'd be splitting the resources. So typically one running instance of Elasticsearch is on one piece of hardware, and that's what we call a node. So you want three servers working together. Your cluster is three servers. Each of them have a running version of Elasticsearch. They team up into a cluster, but each one is individually a node. Then we get down to the data level. So like most SIEMs, right, you're putting logs into some sort of database or whatever permanent storage mechanism. Elasticsearch uses what's called an index. So there will be multiple indices that you will be sucking all of your logs into and storing them there. So when I say index, think database, but it's not quite the same, but it's close enough for comparison purposes. So we'll go with that. Now the way indexes are broken down for a logging architecture, because this is different depending on what you're trying to do with Elasticsearch, we have different indices that are created for different log sources. So we'll have like a firewall index, and we'll have an IDS index, and we may have one for antivirus and everything else that we have. But indexes cannot grow infinitely. So over time, you will also be iterating additional, either by day, by month, by year. It depends on how fast those indexes fill up. The short answer on that is you want 20 to 40 gigs as a size for an index before you should roll it and become a new index. So we'll have different indices, and we name them kind of like this. We put the name of what's in there, and then we put like a date after that. And if we have to iterate it by year or month or day, or we can even put the time, right, if things are moving really, really fast. So different indexes across time and across data sources. They're all ultimately like their own little database. Now, an index is not actually a thing. This is where it gets a little bit tricky. An index is a name for a group of other things, and those things are called shards, right? So you think you shatter the index into a bunch of pieces, all of those shards together make up the contents of the index. But you could take an index for, say, your firewall logs, break it into 4 different pieces, and then you would need all 4 of those pieces to make all of the data of the index. But the cool thing about this is how you split it up across your nodes. So if you have 4 servers, you can break up index, of your firewall logs into 4 separate pieces, throw it across 4 pieces of hardware, and now you can use 4 pieces of hardware to search the same amount of data, so it gets faster. That's one of the great things about Elasticsearch. You can arbitrarily add more hardware, and the data will spread out thinner and thinner, allowing you to search more faster. So that is really, really flexible. Inside each of those shards, oh, and by the way, each shard is actually a running version of Apache Lucene. That search engine that I talked about that's actually under the hood of Elasticsearch. Elasticsearch is a program that makes 4 versions of Apache Lucene kind of work together. Shards have your actual logs in them, but they're not called logs, they're called documents. Everything is a JSON object, and it is called a document. So you bring in Syslog, right? It is a line, it's like 200 bytes long or whatever. what you do is you don't just save that plain text, you're actually using Logstash to break it up into all the interesting pieces. So you pull out the username, and you pull out the time, and you pull out IP addresses and all of that. And that becomes the field in the JSON object. So I'll have pictures of this in a second if you don't know what I'm talking about with the JSON. So why is Elasticsearch so fast? It's because of the shards. This is the magic, right? We are breaking up a database of stuff as many times as we want across as many pieces of hardware as we want. And so when we get more hardware, everything becomes faster because it's able to spread things out with those shards. There's another reason it's fast. For many SIEMs out there, not all of them, because actually some SIEMs are completely built on Elasticsearch. Logarithm is now Elasticsearch, and Exabeam is actually Elasticsearch as well. They both just kind of put skins on it and do a little extra parsing magic in there that's done for you. But outside of those, like Splunk and QRadar and those kind of things, they're what we call a schema on read SIEM, and we call it that because the logs, this is kind of an oversimplification, but the logs come across the wire in their native format, right, as a syslog line or whatever, and in Splunk and QRadar, you store them on the hard drive like that, right? And then when you go to search them, you have to parse it at search time. So it's called schema on read because as we read the log back out of storage, that's when we parse out username and source IP and all that stuff. That's an oversimplification because with those SIEMs, you can't actually determine that, hey, these are some fields that I'm interested in and make them go faster. So that's a little bit of an oversimplification. But with Elasticsearch, it's different. Everything has to be parsed on the way in, or at least should be if you want the fastest performance. So what we do in Elasticsearch differently is we take Logstash, and every log that we bring in has to be broken up into all the fields before it gets stored. And that's why it stores things as a JSON object, because in a JSON object, you can break things up into all of those fields ahead of time. And then Elasticsearch is ultimately a way of recalling logs that are broken up into JSON objects very, very fast because it splits them across all the pieces of hardware you have. So we're doing schema on ingestion. That is the difference. And the other cool thing about that is every single field that you split it up into will search as fast as all the other fields for the most part. There's tiny caveats on that, of course, but any field that you break it up into, you can search equally as fast. With this kind of paradigm, you can only quickly search the things you have predetermined you want to index into a database. So some of the common stuff might search quickly, but the other stuff will not. So how do we do this, right? We have an index. The index is broken into 4 shards in this case, and one of those shards goes onto a node. So we break up these pieces, we put them across our nodes. There's a couple of different types of shards, though. There are primary shards and there are replica shards. So when I say primary shards, think if you have RAID 0 hard drives, right? You have a bunch of pieces, and all of those pieces need to be present for you to have all of the data, right? If one of your RAID 0 hard drives goes down, you lose all the data. That's exactly what primary shards are doing for you. But there's what's called replica shards. And so each one of those pieces of data can be exactly cloned into another shard that has exactly the same stuff and put onto another piece of hardware, such that if you bring down one of those nodes, you will have another copy of that data. The replica shard will become the primary shard. Everything continues to work as normal. So my other virtual machine should be up here. And now I should have this right here. There we go. So what we're looking at here is this. I have the instructions for how to get to this in the Docker container. This is a single node cluster. There is one node that is across this whole row right here on the bottom. These green boxes are primary shards, and these columns are indexes. So I have an index called FileBeat 660 2019 0218, and then I have another one for 0221, and I have this other one and this other one. You can see all of these and the pieces that they're broken into here. So this one has 3 primary shards. A solid box means a primary shard. These gray boxes are replicas that do not exist because I don't have any more nodes. So the idea here is this. If I had more nodes available, there would be additional rows down here, and these replica shards would populate into that additional row. And then if this node went down, this one could become primary. All the data would still be available, and it would still continue to work. If I had a whole bunch of servers, right? If I had 3 servers, or if I had 6 servers, then one of them could go on each of those 6 servers, and now we could use 6 servers' power to search all of that data. And 2 of those things would be redundant, right? Because 0 and 0 hold the same data, 1 and 1 hold the same data, 2 and 2 hold the same data. So if we want to go search something, we have now 2 places to go to if we had 6 servers with 1 box on each. So replicas and primaries. You have to decide how many of each you want. The answer to how many you want is you probably want as many as you have nodes. If you try to make this infinite and think, oh, I'll have 1,000,000 shards, that'll be awesome. No, that's not what you want, because each of them is a running version of Apache Lucene, and it has overhead. So you want about as many shards as there are active nodes in your cluster. And you want a replica shard for each of the primaries that exist. So in this case, let's say we take that data that I just had there. There's 3 primary shards. There's 1 replica shard of each number. So what's in number 1, replica and primary, that's the same data. Primary 2 and replica 2 are the same data. So if the node that primary shard 1 is on dies, this becomes the primary and continues to work. So if we have 4 nodes and we have an index that is broken into 2 different primary shards, P0 and P1, we have 1 full copy of the data on these 2 systems, 1 full copy of the data over here. Everything continues to work if any one of those goes down. Then let's say, oh, we have more money, right? We can go to 6 servers. Cool. We can add 2 more replicas. So we can have primary 0, replica 0, and another replica 0 right here. And then we can have primary 1, replica 1, replica 1. So we have just more and more copies. When you're going to read your data back, think RAID 1 in this respect. The more copies of the data you have, the more places you can go to read it, or you can read it all simultaneously. But the point is, the analogy kind of stays the same. More copies of the data means you can do more stuff at once because you're spreading it over more hardware. It also works for balancing your writes. So what is faster, writing to 1 hard drive as fast as possible or writing to 10 hard drives as fast as possible, right? 10 hard drives can write at a much greater speed than 1. So if we know we have to write a lot of logs incoming very, very quickly, we say when we create an index, break that into like 6 different primary shards. And now 1/6 of the writes are going here, and 1/6 of the writes are going here, and 1/6 of the writes are going there, etc., right? So however many logs we need to bring in, it doesn't matter what the rate is. We just need more hardware, and we can split the writes up across all of those pieces of hardware, which is how it scales for writing. Searching is the same way, except what we can do is have the primary copy here, and then we can have 5 more copies of the entire index if we wanted. That means we could do 5, 6 simultaneous searches at the same time, and everyone would have a dedicated node to use for finding that data as quickly as possible. A shard can take all of the resources of an entire node. So that is the key to remember there. So you want to spread them out as thinly as possible, and that's what Elasticsearch does for you. If we want to have this split up across multiple pieces, now we have primary 0, primary 1, replica 0, replica 1, replica 0, replica 1. Now we can do 3 searches at once, and it will be split across 3 groups of 2 servers, right? So this can go in a whole bunch of different configurations. And there's some logic behind, do you want to optimize for write speed? Do you want to optimize for read speed? The answer to that is, as you are writing, you want as many primary shards as possible. And as you're reading back, you want as many replicas as possible. It's the RAID 1, RAID 0 kind of thing, right? It works the same way. Back to documents. So a document, one document is going to be one of your log files. And it will look something like this. And I know this is tiny, but a single log will be broken up into all of the relevant pieces like that. This is a bro log, which is just a network transaction that is occurring. The document is broken into a bunch of fields. So they're key value pairs, right? What was the duration? What was the source port? What was the destination port? What were the original bytes and total bytes and all of that? These are all of the pieces that are individually being indexed into the Elasticsearch and well, into Apache Lucene, really. And every single one of those you can search very, very quickly. So we have documents that are created from a log file, right? Your log file is a line. We're breaking up into these pieces. They have to become a JSON object. If you look at the actual object that goes into Elasticsearch, you'll see some metadata on here. So there's this index. It's telling you, hey, what index is it in? Logstash webcast 1. And then it has a unique ID associated with it here as well. The rest of the stuff we don't really need to cover here. But there is this other piece called source. Underscore is the way of designating that something is metadata. Everything that was in the original log is in a nested field called source. So that's the thing to know about that. So a field is every individual thing that you have had Logstash cut out of your logs. So for a firewall log, it's going to be source and dest IP, source and dest port, and anything else that you want, right? Usernames, host names, that kind of thing. When you break up all of this data, we're putting it into a database, right? And to have a database act as efficiently as possible, you need to have some kind of schema. So there is what's called a mapping in Elasticsearch. It's basically the exact same thing. You say, this is a date, this is a number, this is an IP address, and all of that kind of thing. Elastic, sometimes you will hear it referred to as schemaless. It's called that because if you throw data at it, it will guess what the correct data type is, but it will guess in a safe way, not the necessarily optimized way. So the better way of doing this is, if you know ahead of time, and you will, and you should, you pre-create a mapping, and then you log stuff into that index with that mapping, and then everything is correct. There's another key concept here with two of the particular data types. For a string-based field, there are two options that you can use. There is text and there is keyword. And this will drive some craziness. If you try to search for something and you don't get results, the reasoning behind that is probably what I'm about to explain here. So, first of all, keyword. Keyword is the type for when you want whatever is in that field to be an exact match, right? So you're typing in Kibana, I want exactly this, and it matches or it does not match. Or you can use wildcards, of course, as well. This would be something like a username or maybe an employee ID number, tags, FQDNs, anything like that, right? It either matches or it does not match. But let's say we have a URL. So something like http www.mywebmail.com/mailbox/mail1.htm. Wouldn't it be nice if we could just type mailbox and find that log, right? That would be an ideal situation. What the text type does will break this up into pieces so that you can do that without having to use wildcards. If you use this as a keyword, you can still find it, but you would have to search for star mailbox star. And it will match, but that's a very, very inefficient search. The text data type is meant for things like email, where you're categorizing large paragraphs of text and everything like that. When you search in your Gmail inbox, this is pretty much how they've categorized stuff. You're like, hey, I remember that one word that was in the email, but I don't know exactly where it was in the email, so I just want to type the word and hope that I find it. That is what this solution is. So whatever you're putting in, it's breaking up, and it allows you to find it. How does it allow you to find it? It pushes it into what's called an analyzer. And this is what an analyzer is doing if you select the text data type, right? This doesn't apply to keywords. Oh, I forgot one key piece here. You can actually pick both, and you should pick both, because you want to do both of these things. Okay. An analyzer, it takes this log URL that you have, right, and it throws it through what's called a character filter. The character filter will strip off the special characters in this case, and this you can actually pick whatever you want for both of these things, but this is what the default will do. So it takes out the colon and the slashes there and the slashes there. It becomes this string, right? And then it throws it through what's called a tokenizer. And the tokenizer, by default, will tokenize things and break them up based on white space. So now, what comes out of the tokenizer are 4 different tokens: HTTP, my webmail, and then mailbox, mail1htm. These are the things that you can search for and successfully find this. If you search for something like com/mailbox, you probably will not find what you're looking for because it didn't get turned into a token. So that's how that works. When you go to search for something in Kibana and you do not find it, it's probably because it did not get tokenized like you'd expect. When you do find it based on a token, it will actually highlight the token and tell you, hey, this was the actual thing that matched. What is it doing with these tokens? This is as deep as we get. The tokens go into an Apache Lucene form called an inverted index. And this is not the same index as the Elasticsearch index. It's an unfortunate overlap of terms. But this is literally what it's doing. It's taking whatever you had in that thing that you have typed as text. And in this case, I'm just going to use 2 sentences to explain this because URLs would be painful. So we have sentence 1, the woman is walking down the street. And 2, the man is walking into the store. We type these as text. What Lucene is doing is breaking them up into these tokens, and it's putting them in this format. What are all the tokens that are possible in all of my documents, and then a list of all of the documents with an X mark if it appears in that document. Why it does this is because we are doing a search based on a term, and we want the answer to what documents have that term as fast as possible. And this is the most efficient way to do it. So we say, you type walking in Kibana, right? And it can say, okay, is this walking? Is this walking? Oh, there's walking right there. And it's in document 1 and 2, pull them back. It's very, very fast at doing that. If you have a schema on REST-SIEM, what it will do is potentially save this whole sentence, and then it would be, in effect, having to walk through the entire sentence in every single log every single time you search, which is horribly inefficient, which is why the schema on write thing is a great way to do it. Question?
How does it parse the data? So space?
How does it parse the data? So in this case, yes, it's broken up by a space. You can pick different tokenizers and character filters. There's actually another thing on here called a token filter that I didn't show because it doesn't actually do anything in this case. But these are all choosable. So you ever type something into Google and you get it wrong, right? Or you type the ing on the end, but there's like a root word and it finds that as well. How does it do that? Google's actually tokenizing things with an English tokenizer that will take the ing off of words and then make it so that you can find that same thing based on the word with ing on the end or es or whatever. It's doing all sorts of crazy games like that. For us, we're not doing that. So there's a whole bunch of different tokenizers and stuff. For us, we don't care about that. So it goes into the inverted index, and there's different types of inverted indices in games that get played for each type of data. The number type, if you type it as a number, it does not do this. There's a whole different way of most optimally searching for numbers. So this only applies for text data types. So here's the top level view again before we switch into talking about Kibana here. We have a node. The node has indexes on it, but the index is really just a name for a group of shards. And the shards are one-to-one with versions of Apache, or instances of Apache Lucene. And then I did not cover segments, but within Lucene, it's actually breaking stuff further down, and then we'll ignore that for now because that's going too deep. Okay, Kibana. Kibana's interface is fairly self-explanatory. There is a bar on the left side that has all of the stuff that you will want to do. Discover, right? This is your main tab for searching all of your data. Visualize will let you create any kind of visualizations you want to make. Well, most of them. There's a few oddball ones in there. Dashboards. The workflow here is this. You make a search, you pick some columns and some filters, stuff you like, you can hit save on that search. You make some visualizations, you hit save on those visualizations. Then you can go to the dashboard tab and say, put all these things together on one particular dashboard, and then filter it all together. That's what I had with the PPA tickets display earlier. When I click on one particular ticket type, it actually filters the whole dashboard for that same term, which is awesome. If you're doing threat hunting, that means you can put up usernames and you can put up IP addresses and domains and everything all at once on one dashboard. Click John on the dashboard, and then it filters to everything that I have done specifically all at once, which is awesome. Timeline is a special way of doing charts. We probably won't get into that. Same with Canvas, that's some new stuff. There's a machine learning module. That is a paid feature. Infrastructure is a way of monitoring through the beats what is going on. So if you have 100 computers all with metric beat installed on them, it is saying how much RAM is there, what's the CPU usage, and all of that stuff. You can click on those and then get a live view of the logs streaming in. That's what the logs tab does. DevTools gives you kind of a REST API style way of communicating with Elastic directly. Monitoring monitors the health of your cluster, and management is to manage your cluster and Kibana and all the other stuff. The Discover tab is the one that you need to know how to use most. The two things that people mess up with most is, one, when you go into the Discover tab, you have to first pick an index that you're going to search. We have to come back to that in a second. Time filter, right? You're searching for something, but this wants to default to last 15 minutes. So why am I not seeing anything? Because you aren't searching the time where the thing happened, right? Then, down the side, we have a list of all fields in the logs. This is another thing that is unique to Elasticsearch. Because you have to parse things on the way in, it already knows all the fields. If you've ever sat at a SIEM that does not parse things on the way in, you've had the problem, well, what did we call the username field? What did we call source IP? Is it src_IP? Is it source.ip? Like, what are all these things? This one lists it for you, so it's really nice. This is the document data, and everything that is in your logs is broken up like this by default, and you can pick special columns to apply to that. I'm going to do a live demo of this here just because it makes for better than slides. So here is Kibana. And I gave you all the newest, like literally released days ago version of Kibana. This is 7.0 beta 1, which is probably a terrible idea. But hey, if it doesn't work, you can all have your money back. So I wanted to show you the very, very newest one. What I've got here are the UFW logs. This is what I passed out as a sample data source. So this happened last week. The time picker is a little bit different in this version. So I go to absolute. I'm going to pick February 12th at the beginning of the day, because that's about when I started recording them, to February 19th at the beginning of the day. Hit update. And there they all are. So you get this histogram view of logs over time. All the fields that are in the logs are over here. This is the full log, right? Maybe I don't want to see that. Maybe I want to see the destination IP, and I want to see, let's see, source IP, source port, destination port. That's how we add columns across the top, right? Fairly self-explanatory. We can shuffle columns around like this. If you want to see a specific log, then all you have to do is click on this one, and it drops down and shows you all of the individual broken up fields that were brought in. This was broken up by Logstash on its way into Kibana, remember. This is the actual format that it was. So here's the log as it hit Logstash right here. I know it's small. A lot of stuff, firewall log. There we go. The original log is stored in a field called message by default. But I applied parsers that broke it up into all of these individual pieces for me so that all of those would get indexed. So that's kind of the idea there. Okay. Inside here, showed you those things. When you unfold this, you can say filter for exactly this. So maybe I want to see transactions where bytes is 566. You can click the plus magnifying glass. You can click the minus magnifying glass if you want to take those out. This is another way to add it as a column you see, and then that is this field must exist. Not every field has to exist in every log, right? If it's not there, it's not parsed out by Logstash, it doesn't show up. So you can do an it exists or it doesn't exist search as well. Index patterns. This is the other thing that's very important and confuses people about Kibana. So you take your logs, you put them into Logstash, Logstash parses them, and it's beautiful, and then it throws them into Elasticsearch. And they're in Elasticsearch, and you can see them in Cerebro. So let's say I bring up Cerebro over here. I have all these things. Great. These do not show up automatically in Kibana. You have to tell Kibana that you want to see these things in a certain way, and then they will show up for you. And that's what an index pattern does for you. So in this case, there's one called Kibana sample flights. Let me see if I can find, actually I'll just undo, yeah, that'll break it. I'll make a FileBeat one. So notice I have a couple different indexes called FileBeat. FileBeat there, FileBeat there. In Kibana, if I actually want to see my FileBeat logs, then what I have to do is go into the Management tab and click the Index Patterns thing right there. And then I click Create Index Pattern, and then I can type FileBeat, and it says, here's the two indexes that you have called FileBeat. Do you want to pick one or the other one? Or, in my case, I want to search them both at once, right? Because these are iterating over time. I don't want to have to click individually for January's versus, February's versus everything else. So I do FileBeat --, and it says, yep, those are the ones you're going to be searching. I can make that as an index pattern. And then you have to tell it, where is the timestamp? Because you cut the individual timestamp out. We say, yep, it's in a field called @timestamp. That's the default. And then in there, we now have this index pattern called FileBeat. That is what makes it show up on the Discover tab. So notice these two right here were specific for just one index. But FileBeat, I can click that one, and now I'm searching several indexes at once. So that's kind of what you have to do to see these logs here. So that's another key piece to getting this to work. Oops, don't want that on the screen. Visualization types. There are many all the things that you would expect. There's area charts and line charts, horizontal, vertical bar charts, heat maps and donut charts, tables, gauges. This is a markdown-based metric. This is a tag cloud. And of course, you got to have the pew pew map, right? You can have the view of everything wherever it is on Earth with GeoIPs. That's a really cool way of visualizing some data. The other thing that you can do is nest your visualizations. So this part is also a little bit complex, but I'll do a demo on this one as well. I try to explain it as simply as possible. When you go to make a visualization, you have to pick a metric, and you have to decide how you want to bucket your data. If you have used something like Microsoft Power BI, then this is something that is very, very similar to that. Think about this. The question you're answering is, I want to see metric per bucket. So you can say, I want to see, you don't want to use bucket at all. I just want to see total bytes, right? That's one way you can do it. Or I can say, I want to see total bytes transferred per username. Or I want to see request count and bytes per HTTP method. Or I want to see requests per user per site. We can nest buckets. That's what this is doing. So if I want a 2-layer pie chart that first breaks it down by user and then by site, I can do that. And then my metric would be how many requests did they make, or what was the sum of the bytes in the metric, or I mean in the actual logs. So we have all these options for bucketing, right? So we take all of the logs and we break them up and we put them into buckets. And then we run a metric over all of the logs that have landed in each individual bucket. So if we have an organization and we want to answer the question, who has used the most bandwidth in the organization? What we would do is we would bucket by username, which would put all of John's traffic here and like all of Leo's traffic here. And then the metric we would run would be the sum of the bytes, because all of my logs for like the proxy or whatever would be here, and then it can go into those logs, pull out the byte count, sum them all together, and spit that back out at me. So we just have to think about how to form the question in terms of how do we bucket it and what are we calculating on that bucket. And that's how that kind of works. So for the firewall logs that I gave you, here's how this looks when you do it live, because it'll make more sense that way. We want to make a new visualization. So we can click on this right here, and I will pick a pie chart, and I will pick my index, UFW logs, and I have the date set right. Right now, there is the metric of count, and there are no buckets. So it's just counting every firewall log that I have, 64,855. But let's say I want to split it into something more interesting. So what I pick, let's say I want to do source IP. I pick terms, and then I can pick the field that I want to bucket by. So in this case, I'll just type it source IP. There we go. And so by default, it will give you the top 5 source IPs, right? Very nice and easy. Hopefully that's fairly self-explanatory in how that works. When I mouse over this, it will give me the count. So now I can see my top IP address by count was 125.91, whatever, and there were 3,856 logs. By the way, where this data came from, I just bought a VPS on DigitalOcean and turned on high debug logging basically for the firewall, and this is just the internet scanning my random VPS. So it's all real data captured in the last, February 12th to 19th. If I want to bucket this in another way, let's say I want to answer a different question. Let's say the question I want to answer is, which IP has scanned me from port 22 or to port 22 the most? So who's trying to brute force my SSH, right? We have to split this up differently. We can say terms, and then we can say destination port, and that will break it up into this, right? Actually, let's go with 445 because that's the top hit. So SMB scanning, right? Who's scanned me the most for an SMB port? That gives me the port number, but we also have to do a nested bucket where we say terms again, and I want to have the source IP. There we go. Here is all of the 445 scans. Make this a little bigger. Here's all of the 445 scans, and this is the top IP address that was causing them. So 119.159 is the second most common IP address that was scanning me, third, fourth, fifth. Here's my second most common port, 2222. That was actually the one I was administering it from because I had a port 22 honeypot up. So that's probably me, at least in part. Port 80 and all of that. So we can continue to nest these as many layers as we want and put these all together. So it's really, really cool in that it can do that nested bucketing for you. All of this stuff goes on the dashboard and allows you to filter however you want. So you can bucket by more than just the field names. You can bucket by a search if you want to do a filter for that. You can bucket by time, so effectively giving yourself a date histogram. You can bucket by IPv4 ranges and other various things as well. A lot of different options there. So I just did the demo. Now, one thing that I need to point out, Elasticsearch has no security by default. If you put one of these up and you put it on the internet, you're probably going to run into this message one day, right? And you don't want to be that person that just got all of their security stuff encrypted. Of course, it would be insane to put Elasticsearch on the internet, but hey, people did it because this happened in 2017. This was an Elasticsearch worm that was cruising through the internet. You go to Shodan, look for what port 9200 is open, and there's going to be probably thousands of them. And if you do not take active action to lock down your Elastic cluster, which I will tell you how to do in a second, this is probably what will happen. So there's no RBAC, there's no logging in, there's none of that stuff going on unless you take action to do that. So here are your options. The noob mode option, which I really, really don't want you to do, but I have seen done and I highly discourage it. Put an Nginx reverse proxy in front of it and just make people do some kind of basic authentication to get to the web page. You don't have any kind of role-based access control. Every single analyst and every person that accesses the cluster can still delete everything. You just have one password for everyone. Terrible idea. But you can do it as an absolute minimum, right? If you do not want to pay to lock down your cluster, there are two third-party programs. One is called Read Only Rest and the other is called SearchGuard. These have a community version, both, and they have a paid-for version that will allow you to lock these down. The downside of this is it will take you some labor. They are cheaper than this option, which I'll get to in a second, but they probably don't release as often, and it doesn't integrate as deeply as the one built by Elastic, which is what this one is down here. So you can do it for free. It will just take a little extra work, so time-money trade-off, right? Down on the bottom, if you pay for the commercial features from Elastic, you can get what is called security, and it's basically like click, you're done. So it's awesome, it's integrated. As soon as they update, this immediately works with it. If you have the funds to do it, this is what I would highly recommend you go for. But I do know a lot of people using these other two options and having success with it as well. Logstash. For Logstash, it is a program that takes in logs from any format that you are interested in throwing it at, and it is really, really good at taking in literally almost every format. It will take them in from Beats and the Beats protocol. It can take them in from Syslog or anything else. And then it will integrate well with those. It'll push them out to Elasticsearch. But you can also push them out to anything else you want. There's a whole bunch of plugins. I'm going to pull up the Logstash website real quick. Search Logstash plugins, and you will see this page right here. And down on the side, these are just ways that you can input into Logstash that are built in, right? So Azure, Elasticsearch as an input, not as an output, right? Files and GitHub, and I don't know what some of these are, IMAP, HTTP, databases, IRC, Kafka as a broker, Redis, and everything else, right? Tons and tons of options. Same thing for output plugins. A lot of options here as well. You will almost always be using Elasticsearch as an output, but you can also have it output to other various things, which we'll explain why you might want to do in a second. Then there's what's called filter plugins that we'll get to in a couple slides here. These are the ones that are actually doing the parsing for you. So if you're throwing in a CSV log, you can call this plugin called CSV. If you're putting in a key value pair log, you call KV, and it just automatically tears it all out for you. It makes it very nice and easy to do this. So Logstash sits between Beats and Elasticsearch. We throw whatever we want at it. It parses it. It uses one of those input plugins to receive it. It uses a filter plugin to parse it. It uses an output plugin to send it, one, to Elasticsearch, and two, to anything else that it's compatible with that you want to send it out to. So multi-in, multi-out. How do you use this in your environment? You will have probably more than one instance of Logstash. You can have various Beats agents reporting directly to a cluster of Logstashes. These don't talk to each other. I use the word cluster there. Don't think they're like joining together like Elasticsearch. They're all independent in this case. And then if you have other stuff you want to do load balancing with that doesn't support Beats, of course, you can do that as well. Send it to a load balancer. Here's how it works. The input, filter, and output plugins. When you go to create a Logstash configuration, this is what you are looking at. What is the input? What is happening to it in between? And then what is the output? This is the parsing mechanism here. So if we look at a Logstash configuration, this is what it looks like. We have an input block up here on top. I'm saying I want to use the TCP input plugin, so I'm just listening on port 999. I want to use the standard in plugin, which takes no arguments, so I'm just listening on standard in. I can type in the terminal. And then I want to use the Syslog plugin, which will listen on port 1514. And when it sees Syslog, it can actually tear apart the header a little bit and do some work for us right off the bat. There's no filter plugin in this. This is just a demonstration. And then an output, there's a standard out, so it will print it back out to the screen if you want to see it. That's not something you would leave on in production. And then there's the Elasticsearch output. This piece being here is how you connect Elasticsearch to Logstash. So anything that goes in to here will end up being in an index called my first index. And all you have to do is say, what's the IP address of Elasticsearch? What's the index you're writing out to? So it's not too complicated to get that going. So here's the config file. I just showed you this one, well, a similar one. This is the one I used to parse the PPA tickets. We have a CSV. So it was basically just a CSV file, violation description, and all of that, right? What was the list of all the columns? I was skipping empty columns. I was skipping the header lines. And then I was outputting it directly to Elasticsearch with an index called PPA tickets on the bottom there. I use TCP with port 9999 when I want to do like just some kind of single file. What I used was netcat, so I just use redirection from the file to netcat, localhost, port 9999, throws it all in there. Very easy way of doing that sort of thing. So I'm going to skip that one until we get to the end. Input plugins that you will probably use. Beats, right? Anytime you use a Beats plugin, you just say Beats, open bracket, close bracket. You're pretty much done there. You can change the port if you want to. Syslog, file input if you want to pull something off the hard drive. HTTP input if you want to receive things with that. TCP, UDP. You can also use Elasticsearch as an input. If you want to pull logs out of a database, there's JDBC and SQLite. If you want to send back and forth from a message broker, there are Kafka, Redis, and RabbitMQ plugins for inputs. For filter plugins, the main ones you will probably run into: CSV, Grok, which is a way of doing regular expressions, key value pairs, JSON, and then you can do a Syslog PRI, which will parse out the little angle brackets in the front that tell you a facility and severity, XML, date, things like that. You can use it to drop any kind of logs that come in. You can use conditional logic and say if event ID equals whatever you don't care about, drop. And then you can do enrichment, which is awesome. Enrichment lets you do a DNS query. You can do an Elasticsearch-based query on one of the fields in your log. You can do the GeoIP thing, which is what I have in the demonstration, only you're doing it with Elasticsearch instead of Logstash. There's mutate, there's REST API calling. We can parse out OUIs from MAC addresses and user agents. This will take in a user agent and it will tear it apart into all of the browser versions and the operating system and make those all individual fields, which is really cool. TLD will tear apart a domain name into the com and like google.com and www and Google and all the various iterations that you can make there. And then you can actually just say, hey, run this Ruby code on whatever's in there. So literally anything you want. That makes Logstash an arbitrary log manipulation engine, because if you can write the code, you can do it in Logstash. So the original log is going to stay there in that message field. But after that, you can do whatever you want and add all those additional fields. For output plugins, we have Elasticsearch, of course, and then we have standard out, which is what we use for debugging. Third-party applications that you may want to throw stuff at, you can do alerting directly out of Logstash if you want to with any of these. For example, simple notification service. You can send yourself text messages based on your logs. I have that set up at home. What you will probably run into with your logs is Syslog, right? Everyone has Syslog, but Syslog is the worst. Why is it the worst? Because we have this nice header on the front, right, that we know is always going to be there, but everything that comes after that is like total unpredictable disaster in a lot of cases, right? Your firewall log is going to say one thing, your syslog for whatever else you do on the system, it's going to be something totally different. So you have to write all these separate parsers. And the way that you would want to break this down in Logstash is you would feed this through several different filter plugins in a row. So you would have one plugin that could tear off the header and put the date in there and say, oh, it came from a machine called logparse and it came from sudo, and then here's this message field. And then the message field is where you would have to then apply some other kind of regular expression to make that parsed into something that you were interested in seeing. So we don't like Syslog because it's unstructured and unpredictable. There is a plugin called Grok, which makes things very, very nice and easy to use. Instead of writing a regular expression, which we all know reading someone else's regular expression is literally the worst thing on earth, right? It takes regular expressions that are written for you already, that are solid and good, and gives them a name. So you can just say IP address and match an IP address, right? You don't have to try to decipher what an IP address regular expression is. Trying to do that is ridiculous and almost impossible. So Grok makes it much better. Ideally, when you can, we want you to use new log formats because that parses automatically. We use the word extraction for that. We say that because with these plugins, right, CSV, key value pair, and JSON, the fields are already defined. So all you have to do is say, this is key value pairs, and anything there's a this equals that, right, that becomes a new field in your log automatically, and you don't have to do any kind of parsing at all. So it's very, very fast and easy. JSON is the best. That one is the most dependable in terms of logging. We recommend everyone move everything into JSON logging where possible. CSV is the least dependable, but it's also the most compact. So that's kind of the spectrum there. So here's your CSV filter plugin, right? The thing in the box would be the log that we threw in. The thing on the bottom is what the plugin would look like in Logstash. So we just say, we're throwing in a CSV, and the columns are going to be in this order: source IP, source port, test IP, method, virtual host URI. We throw in this, and it knows exactly what order each one of them is. Every single one of these becomes a field in that JSON document that goes into Elasticsearch. So nice and easy, right? Key value pairs are even more simple because we don't even have to list column names. We can just say it's KV pairs, and it's split with equal signs, and the fields themselves are split with a space. So now we throw in a log like this. The blue ones are the keys, and the red ones are the values. And immediately we have a source IP field and a test IP and an action and all of that. No work, right? Very, very simple to get done. Here's an example of how this would work if we had syslog with KV inside it, right? We have a header up here in blue, and that's where we call syslog input, and then we could have the rest of this stuff feed into the key value pair, and it would parse out the additional info. So user is root. That came from right there. User equals root. Command equals bin su. So command bin su, right? That's basically what you have to do there. There's a little bit of detail that I left out there for the slide, but it's basically that easy. You just have to take it apart piece by piece. JSON is the simplest. We just say there is JSON coming in, and the source is going to be in a field called message. Done. All your logs are parsed, right? It's the greatest thing ever. So the whole Elastic Stack in a nutshell here. What we have, we send all of our logs in whatever way we want to Logstash. Logstash, we set up an input plugin for however we have decided to send those logs. It can be TCP, UDP, beats, HTTP, and databases and everything. We bring them in, we parse them out with CSV or Grok or KV or JSON or whatever it takes, all down a row, right? And you can stack all those up as many steps as you need to do, parse them into those fields. Then you can enrich them, which I wish I had time to talk about, but I don't. Enriching is the most awesome part of Elasticsearch or of Logstash, because it makes your logs that are really, really boring really awesome, because you can bring whatever you want in from the external world, and then you can put that in there. Then this big JSON document gets put into Elasticsearch, and we're searching it with Kibana with our queries. Default ports, the last thing, this is, again, the high-level overview of what's going on. Beats, by default, will use port 5044 as a destination port. So if you want to do that, you call the Beats input plugin. Logstash will receive it. It will send it back out. Elasticsearch listens on port 9200. You can go to port 9200 in the browser and see that it will just respond with the JSON object, says, I'm this cluster and I'm here. Kibana, you access it through 5601. Kibana then turns around and accesses Elasticsearch again through 9200. And if you have more than one node of Elasticsearch, there's some other different ports that are in use, but it's not really a big deal for our concern because that kind of all happens automatically. Now, the last thing I want to talk about, because some of you probably have SIEMs already and are curious about Elastic, right? That's what I see a lot in the class that I teach. People are like, well, we're paying a whole lot of money for our SIEM, and we heard this Elastic thing can be done for free or very, very cheap. How do we make that transition? Here is some architectures that you can use to do that. If you take your logs and the way that you are bringing them now, you adjust to put Logstash in the mix. you can still send the logs as you have always done to your commercial SIEM without the SIEM even knowing anything happened. But you can also send them out to Elasticsearch. So step one of migrating, or at least sampling stuff, or getting it to go to two places at once, Logstash is a great way to do that, right? Multiple outputs, they're queued and all of that, great way to do it. If that doesn't work for you, you let your logs go into your commercial SIEM, and then you use Logstash to pull them back out, and then use that as an input and then an output into Elasticsearch. Most SIEMs have an API that will allow you to do something like this, or you can set up a forwarding destination for everything that goes in to just continue it on through and send it to Logstash. So that makes it really easy as well. The other way to do it, which is actually my favorite, but it's more complex, you use a log broker. So this is like RabbitMQ or Kafka. Kafka is like the beast of the log brokers. If you don't need it, then you shouldn't use it. But if you need like a million EPS, it can totally handle that sort of a thing. You take your log agents, you take your logs, you do whatever. You get your logs into Kafka however it takes. Logstash can help you do that because there is an output plugin for it. Then you have your commercial SIEM pull out of Kafka totally independently of your Elastic stack, also pulling out of Kafka at a different rate, different data, whatever. Kafka is just storing everything that goes into it until you're ready to delete it. So it is just a very, very high performance log buffer that you can get as much space as you want to do this sort of thing. Okay, this is from Elastic's documentation on best practice architecture. So this is the full view. We have beats. We install beats everywhere we can. Everywhere we can't, we send directly into Logstash or into some kind of queue with Kafka or Redis, any kind of messaging queue that we want. We take Logstash. We run as many versions of Logstash as we need to support the events per second that we're trying to collect. We just scale them out and we can load balance stuff to them like was on that previous slide. Everything here goes into an Elasticsearch node. What I didn't have time to cover is that there are different types of nodes. There are master nodes. Master nodes basically keep the cluster alive. So you need to have dedicated master nodes to do that. And then there's what's called data nodes. You can split data nodes up into hot and warm, where like maybe SSDs go on the hot nodes and every log you collect stays on a hot node for 1 week and then you age it off onto a warm node or something like that. There's various other node types as well that aren't as relevant to us. Machine learning would be another one, or alerting. But some of these other ones don't have time to go into now. But if you dive in with the solution, you can easily read about that. So with that, I think I have ended right about at 1 hour. But I can show you some other stuff on here. But I think that is the end of the presentation, unless anyone has any questions on that. I know I went quickly. Yes.
On the architecture that you just showed for Elasticsearch,
Yes.
what's the basic equivalent of the correlation engine and the rule? Is that the query you run or?
So correlation rules. So if you want to write like for when something goes to a bad website or whatever, yeah. So those can be done in a number of ways. There is a tool called Watcher that is one of the commercial features of the Elastic Stack, and it is a learning engine, and it helps you do that. Sorry for the Elastic employee in the room. I don't like Watcher. It's very, very confusing. I talked to other people from Elastic, and they're like, yeah, we understand. And I think that is potentially being remedied in the near future. However, there's another tool called ElastAlert. Yelp wrote it, and it's a free open source one that you can use for alerting on your own. And I actually like the format of the rules a lot better because it's a lot cleaner in terms of how you can write and understand what's in there, whereas the Watcher version is a lot of curly brackets, and it's not very straightforward. So 2 different ways you can do it, the paid way, the free way. I actually like the free way a little bit more. Any other questions? Yes?
So ballpark on resources, like if you're just learning this on your own, does this require 64 gigs of RAM to set up just a lab to play with?
Not at all, because that's what that Docker Compose script is for you. That is running Kibana and Elasticsearch. The instructions that I gave you in that GitHub repo will use what is called actually an ingest node, so we can skip using Logstash and import that firewall log directly into Elasticsearch from the Kibana UI, which is something they've recently added, which is awesome. So on your laptop, not a problem at all. If you're trying to throw in like gigs and gigs of data, then you're going to probably need something more than that. But the recommendation for a node size in a production scenario is 64 gigs of RAM. And you can say 32 gigs go to Elasticsearch, 32 gigs go to the OS. And then you strap as many of those together as you want in your cluster.
Okay, that answers the question.
Yep. Anything else? Okay. Oh, yes. The slides, I haven't decided where I'm going to post them yet. It'll probably be on SlideShare. I'll update the GitHub repo when I get them posted somewhere and just have a link to it. And then whatever I put on YouTube, I'll put the video on there as well. So, okay, that's all I have for this. I'll just do some like playing around up here with the stuff up here, but don't feel like you have to like, I'm not going to be in presentation mode. So move around the room and do whatever you need to do if you got to go. So I will pull up.
Just to show, okay, so we got the demo. You guys,
Awesome.
you guys running the Docker image?
In terms of like an operating system?
Yeah.
Mac?
Mac?
Any Linux?
Linux?
Which version? Okay. Okay. We had a couple people that had Kali, and I wasn't sure how to install Docker on Kali, and it seemed harder than it should have been. Okay, good. So, yeah, I'll totally, like, once I do a few things here, I'll walk around and help anyone that got stuck on that part or answer any other questions or whatever. Yeah, I'm sure some people have to go. Yes. So here is what Logstash looks like. I'll pull it up in here now that I have a free moment. Have a good one. So if you download and install Logstash natively, which is what I would recommend you do, the Dockerized version of Logstash, unless you understand Docker, is going to be confusing. So download the real Logstash. I put in the GitHub repo this file called, I think it's simple.conf or sample.conf or something like that. But it's what I'm using here. I'm starting up Logstash here. It's a Java program. It takes a second to spin up, and as long as I don't have any typos, and I don't, I can show you what Logstash looks like here. So I can take a log, or in this case, standard in. I'll just type some stuff, hit enter, and then it says, yep, here we go. This is what I would turn it into. So we have a message field. That's what I just typed. You have a timestamp it came in, the host it came from, and then a version number, which don't worry about that. I'm also listening for syslog input on port 1514. So what I can do is go to another tab and type netcat localhost 1514. This is actually, I'm not going to do it like that because that's going to be too many logs. Tail var log off.log pipe netcat localhost 1514. There we go. That will use the syslog input in Logstash, and now you can see whatever my syslog had in it here. I've got now a facility label to parse that out for me. I don't know why there was a failure there, but that is fine to parse that anyway. The severity label, the host it came from, the priority, and all that has a numeric value. All of that information is there. And that is going through this right here, whereas when I typed it on the screen, that was going through that particular input. Or I can use port 999 and just send stuff to it. So echo, hello, netcat, localhost 9999. There we go. All of these are not having anything filtered out because I'm just sending random garbage through it. But what it is doing is outputting out to the screen, which is what we see right there, and then also outputting to Elasticsearch. So if I go over here, this is the index it's outputting to. So you can see it just created this now. My first index, there are 12 documents in it because that's just what I sent there from the terminal. And if I go into Kibana, now I can add management, index pattern, create my first index. And there we go. And if I click that over here, now I can see it. And need to use 2 minutes ago. What? Ah, bug. I can't get there. All right, let's do it this way. There we go. So this is all the stuff I just imported directly from that Logstash instance running there. Now the thing I gave you, let's see, there's the one where I typed hello, right? So that's how it came out in Elasticsearch. I mean in Kibana. In the dashboard, this is what I've given you. I made a pre-made dashboard of all of the information from the firewall logs, which I now need to, no I don't. I now need to, I now can filter on however I want. So I have it counting it, I have it showing on Earth where all those GeoIPs were from. I have it count by country and port. So I can see here Lithuania was the top scanner of me, and they were scanning on port 8880 for whatever reason. I don't know. And then 300, right? And 3393 and other various things. So Russia was interested in 8080 and 3389, so RDP connections, and port 22 and 4145. I don't know what that is. Down here is another chart where you can do annotations. So I had it actually printing out, hey, there was an SSH connection attempt from, and then it pulls it out of the log. So you can do a chart like that. Let me zoom in on this. And it shows you, if you want to see just 445 or 5060 or whatever it is, you can click on one of these and kind of knock those around. This is a heat map based on source IP. So this right here is scans over time. Can't make that go away. There we go. So this is a histogram with the x-axis as time and the y-axis as the IP address. So we can kind of see from every individual scanner who is causing the most noise. So whatever 125 was didn't really exist at all, and then boom, it popped on the scene there. And then it showed up and did a whole bunch of stuff and then disappeared again. That's a pretty cool way of viewing that kind of data. And there's another one here for ports. So you can see right there, port 445 was scanned very, very heavily compared to everything else. That's actually atypical to what I've seen before when I did honeypots on a VPS. They were really, really after my 445, which I unfortunately didn't have an actual pretend service there. It was a closed port. But you can see 445 and 5060, that's a SIP port, remote desktop, and all that kind of stuff over time. What else? Top IPs by percentage of at that moment. So we can see that giant spike right here from 125. I was just playing with various visualizations you can do here. And then this is the actual search. So let's say I want to look at traffic from Lithuania. You click that, and then it filters it down. And then boom, what I've got now is only Lithuania shown, only the scans down here, only the heat map is relevant to those IP addresses, which you can see now are, let me blow it up here, all 185.254. So that's probably a Lithuanian GeoIP, resolution there. And then I can see by port over time. So if they were sequentially scanning ports, you might see it go across like that. There's various other things that you may or may not see, but you can kind of just dream up whatever you're interested in. And then, oh, I wonder what's actually in that log. I can pop it open right here and look at it. So very, very functional and useful as a dashboard. Pretty cool stuff. I think that's all I've got for you, but this is the data that if you follow my instructions on GitHub, you will have in there, and you can play with all the visualization methods. And the last thing I'll point out is if you want to import your own data, there is a tool here. It is experimental. It works most of the time, but not all of the time. I have managed to break it a few different ways. With a limit of 100 megs, you can import a file, and like you see in the demo, it will try to guess the format, and then it will bring it in and make an index for you. All right, that's all I got. So if anyone has any questions, I'll wander around and look at stuff. But